Okay, when you're dealing with the distribution rule, the easiest way to do it is just to have the students take shapes and go ahead and create the shapes. So you give them a worksheet like this, and then you ask them to represent these shapes in two different expressions and then simplify. So for instance, these are squares, so you have two squares and one triangle, and then you have two squares and one triangle again. So the different representations could be 2S, where S stands for squares, and 1T, where T stands for triangle, instead of it writing out. So you have two squares and one triangle twice. And when you add these, two squares gives you a total of 4 squares, and one triangle gives you 2 triangle. Now this is also a really good way to start inserting variables into the kids' thinking without freaking them out, because the S and the T actually have a meaning, so they get used to the idea of letters being part of the description. Which is actually a great introduction to algebra without actually doing algebra and panicking them. Okay, so, and it also enforces the idea that like terms are combined with like terms, because you can't, you're not going to add squares to anything else but squares and triangles to anything else but triangles. But this is really geared at the distribution rule. It doesn't really involve algebra specifically to the point where the kids can't get it, even if they haven't had it. It's just basically a representation of shapes. So what you have here is, after you've seen you have two squares and one triangle twice, what you have is this 2, and this is where you look at this 2. You have two sets of 2 squares and one triangle. And that came from the 2 squares and one triangle, which gives you 4 squares. We know that gives you 4 squares and 2 triangles. So you had 2 of the squares. 2 times 2 is going to give you 4 squares. And then you just had one triangle, but you had one triangle twice. So again, this 2 is going to end up giving you 2 of these, which gives you 2 total. Okay, so I'm going to go and get rid of this, because this is kind of that's redundant at this point in time. Then you go ahead and back up and do it the opposite way. For instance, now you're going to say, okay, you have one rhombus and 2 trapezoids. This is also a nice integration of geometry into your algebra, into your properties of addition and subtraction. So you've got one rhombus and 2 trapezoids. You have another one rhombus and 2 trapezoids, and you have another set. So you have 3 sets of one rhombus and 2 trapezoids. What does that look like? Well, that looks like one rhombus and 2 trapezoids 3 different times. So you have one rhombus, which gives you a total of 3, and you have 2 trapezoids 3 times, which gives you a total of 6. So you can kind of show how this 3 multiplied, what it's happening is this 3 means you got 3 of each of these. So the distribution process, instead of drawing the arrows, you're basically seeing that this is 3 times everything in here, which gives you 3 sets of each of them. And then you go ahead and let the kids finish this on their own. And they can use, just tell them, these are obviously triangles, so they want to use a T for triangle, something simple. So they have to represent it both as a list and as a quantity with a number. So we have 4 of these sets of the same thing, so you have 4 of these sets of the same thing. Alright, the idea being, which gives you 4 sets of 1 square is going to be 4 squares, and 4 sets of 2 triangles is going to give you 8 triangles. So they can start to see that number is telling you that's how many of what you have inside the parentheses. So they're distributing without actually calling it distributing, which is going to be a little more intuitive. And then you can even introduce double variables. I mean, this is just a worksheet that's actually an algebra worksheet, but it would work fine for this. So now what you have, here you have 2 hearts, a circle, and these are pentagons. So you have 2 hearts plus 1 circle plus 2 pentagons, and then you have another set. So how many sets? Well, you have 2 sets of 2 hearts, 1 circle, and 2 pentagons. So you have 2 sets of 2 hearts, so the 2 hearts gets doubled to 4 hearts. You have 2 sets of 1 circle, which means that's going to give you 2 circles if you have 2 sets of them, and you have 2 sets of 2 pentagons, which is going to give you 4 pentagons. So again, the shapes give them an actual physical manipulative to fool around with, and they can use their own shapes to make different numbers. This was more advanced. I don't know if you'd want to go here, but just to show you, you have a heart and a circle, so you get HC. And this is a good way if you ever have a chance to introduce double variable expressions, because again, it's going to make sense to them because they're looking at a picture that's a heart and a circle. Here you have a square and a triangle, so that becomes ST or TS, and then you can talk about, does it matter? Not really, the commutative property, because they're triangle and square regardless of how you write them. And then you have your rhombus and your circle. And so then again, you've got 2 sets of these. So you have 2 sets of 3 hearts and circles, 2 triangles and squares, and 1 that's supposed to be R. That's D. I was calling them diamonds, and then I realized I should have been calling them rhombuses. So everywhere you see a D, that has to become an R. Okay. And that ends up giving you what your final answer here is. Okay? So, and again, 2 sets of 3 gives you 6. 2 sets of the 2 triangles and squares gives you, whoops, that should be a 4. Evidently I can't count. So let's see. Actually, at this point in time, it wouldn't be a bad idea maybe to make a mistake like this, because sometimes making mistakes is the best way for kids to learn. You say, okay, is this correct? And then let them figure out, and if it's not right, explain to me it's wrong. And hopefully, if you had, if I had left this as a 1, and this is actually an excellent way to teach kids, is to have them do what's called critical analysis and error correcting. So if you had left this actually as a 1 and a 2 and said, okay, is this correct? That would be a great way to see if they were really catching on. Hopefully they would say, well, no, you're supposed to have 2 sets of the 2TS. And then you can say, oh, okay, so therefore, hopefully they would catch that this is supposed to be 4. So it's actually, I'm going to leave this as a mistake because I think this is actually a great teaching tool. They can actually start seeing that, that this 2 has to be 2 sets of everything in here. And right now I've only made 2 sets of the first one, which I think would be a really good process for them to understand how to do that. And then finally, this was an example that I did to show like terms. You have a rhombus and a triangle. A rhombus and a trapezoid, and you have 3 of those. You have 3 of these 2 rhombuses and trapezoids. You have 3 of these. This is a circle, rhombus, and pentagon. And this is also circle, rhombus, and pentagon. And I wrote them in different order anyway, where you can talk about how the order doesn't matter because these are exactly the same shapes. They just, they're just in different order. Like you hear the trapezoids in the middle and the circles in the middle, but it doesn't matter because these are the exact same combinations of shapes. And again, you have 3 of them, so you're going to have 3 of these 2 terms. So you can use just numbers now, which is probably what you want to do. So then you would ask, what does 4, parenthesis, 2 plus 5 mean? Well, it means you've got 4 sets of 2 plus 5, right? So you can do it. You can show that one of 2 ways. You can say 4 sets of 2 plus 5 is going to be 7, which is going to be equal to 28, right? Or you can say I have 4 sets of 2, which we got from up above, what we're looking at. I have 4 sets of 2 plus 4 sets of 5. All right. Oops. So the question is, what is that equal to? Well, that's going to be equal to 4 sets of 2 is going to be 8, and then I'm going to add that to 4 sets of 5, which is 20. And the whole point is you're saying sets of. Instead of trying to do the arrows with distribution, you're saying sets of, and when you do that, you get 28, which gives you exactly the same number, which proves the distributive property, as well as this. This is kind of proving the distributive property. All these are up here too. That it shows that when you add these singularly or you add them as a distribution, you get the same answer. So you can do this with straight numbers. It's actually better to start with the pictures because they have a manipulative to work with, and so when you go to straight numbers, it's going to make sense to them because they've already seen how when you group these as pairs, you get the same thing as this. And then it makes more sense when you talk about, well, you can look at this as putting this together and adding them first, which is what you're doing here. You're adding these together and you're adding both sets. Or you can look at it as this with the distribution property, where you're distributed. Let me go ahead. So you would do 4, parentheses, 2 plus 5 equals. Okay, so those are the 2 ways to see it, and then this would be an equals as well. So both answers give you the same final answer, which is what you're looking for. And then what I would do is I would have them reverse that. So what does this look like in pictures? Well, I can't draw with my my mouse, but basically what this looks like is you have two sets of 3 S's and 4 T's. So what does 2 sets of 3 S's look like? Well, that's 3 S's and 3 S's, so they could write 3S and 3S. That gives you 6 S's. And then you have 2 sets also of the 4 T's. 2 sets of 4T is a 4T and a 4T, which is 8T. So, once again, you're showing that the distribution property, what you're showing is that you've got this many sets of the quantity. And you could do the same thing here. 3 sets of 1M. I don't know what M would be. I guess that could be, what is M? I don't know. It can be anything. Hearts, I don't know what M would be. I'm not sure why I put that there. But anyway, and then R could be rhombuses, or you could let it be anything. Roses, and those H could be hearts, and M could be mice or something like that. I mean, you can actually draw pictures. You can do this with giraffes, animals from a zoo. But the bottom line is this 3 in front means you've got 3 sets of what's inside here. So you've got 1M plus 2H plus 3R, and another 1M plus 2H plus 3R, and another 1M plus 2H plus 3R all together. And that gives you your answer. So it kind of shows the distribution process without the arrows, because the arrows are confusing.